here's something interesting about the difference between absolutely convergent series and conditionally convergent series. If we rearrange the terms in a finite sum, then the sum remains the same. But this isn't always the case for an infinite sum or an infinite series. It can be shown that if a series is absolutely convergent with some s, say, then any rearrangement of the terms of the series in the sum gives you a series which is convergent and also has some s. So rearranging the terms of the series gives you the same sum if the series is absolutely convergent. On the other hand, if a series is conditionally convergent, then for any real number, there's some rearrangement or reshuffling of the terms of the series so that the sum of that shuffled series is equal to r. For example, the series, the sum from 1 to infinity of minus 1 to the n over 2 to the n is absolutely convergent. And in fact, it converges to 2 over 3. We can figure that out from our knowledge of geometric series. And any rearrangement of the terms of this sum will give us the same sum, 2 over 3. On the other hand, the alternating harmonic series is conditionally convergent, and it can be shown that its sum is the natural log of 2. And in fact, we'll probably get to this later when we look at power series. Well, we have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, etc., as the natural log of 2. And now I'm going to rearrange the terms a little bit. I'm going to take the positive terms in blocks of 1, followed by the negative terms in blocks of 2. So my new series is 1 minus 1/2 minus 1 over 4, plus the next positive term 1 over 3, minus the next two negative terms, minus 1 over 6, minus 1 over 8, plus 1 over 5, minus 1 over 10, etc. And now we can pair each positive term with the next negative term, and I get 1 minus 1/2 minus 1 over 4, plus 1 over 3 minus 1 over 6, minus 1 over 8, etc. And I see that if I combine the terms that are in brackets here and I pull out 1/2, I get 1/2 of my original alternating harmonic series. And of course, the sum of this must be 1/2 the sum of the alternating harmonic series, which is 1/2 the natural log of 2. And now I could perform the same operation on the alternating harmonic series in brackets here, and find that the sum of this series is also equal to 1/2 times 1/2 times the sum of the alternating harmonic series, which is 1 over 2 squared times the natural log of 2. And by applying this technique over and over, I can rearrange the terms of the alternating harmonic series to give me a sum of the form the natural log of 2 over 2 to the n for any n.